Okay, welcome everyone to this final session on analytic theory of monoidal categories. So part number 5, which really means there are 4 parts before this. So it actually will be reasonably self-contained, but maybe not quite. You get the point. And yeah, my strategies to avoid counting today are really, I kind of would really like to address the same question as before, but now in a general monoidal category, whatever that means. It will be a bit more precise as we go along. And what we will see is something quite nice, namely some random walk type object here. So this is well, maybe one can't see that, but this is like how a random walk in 3D would look like. So random walk, you choose all the 6 possible directions. I will only draw 3 of them, or all the 6 possible directions equally likely into just some more random walk like on the integer lattice. And you get some pictures like this. So 3 different random walks, a blue one, a red one, and a green one. Anyway, so this is related to the analytic theory of monoidal categories. If that isn't clear, don't worry. The whole point of this video is to hopefully make this clear. But as usual, I here with my reminder, log plots, and we are interested in the number of indecomposable summons. And I essentially did it for groups. Yeah? And the question that immediately comes to mind, if you go back, and I claim very broadly here that I'm looking at monoidal categories. Yeah, so the obvious question that comes to mind is, what about monoidal categories actually? Can we say something about monoidal categories? Yeah, rep G is the one I was using here, representations of a group. That's a really nice example of a monoidal category. But can you say something in more generality, right? Can you say something about a general monoidal categories or something? And the assumptions I have are kind of really, well, additive Krull-Schmidt. What does this mean? This essentially means my problem makes sense of decomposing this space, right? We want to decompose this space, decompose, I guess it's spelled like this, this space into indecomposables. And in order for that question to even make sense, I need a tensor product. Fine, I'm going to study monoidal categories anyway, but I also need addition, and kind of the notion of indecomposable should be somewhat unique, and this is just what those 2 adjectives mean. Very harmless. I probably don't need k-linear, but I will assume it. Anyway, so these are like the minimal type of assumptions to even make sense of my problem. And as usual, it will be, or as in the previous talks, it will be like the surprising or beautiful answer in the end is that you get nice answers even in some ridiculous generality. And this is like really general. I essentially make sense of my problem, and in that kind of generality I can tell you something about it, which is like really exciting. So keep in mind that kind of the easiest and most general thing we had was the beta theorem. So the overall growth rate, the dominating growth rate, is always the dimension. In what sense is that even true in general? To make sense of this assumption, somehow you need to make sense of the notion of a dimension. And let's say the minimal assumption I have in this case would be just a functor to vector spaces from my parent category. So I have some parent category C that I want to study, my additive Krull-Schmidt monoidal category, whatever. But I don't have a notion of dimension yet. So I just send it to vector spaces. And every object, then you can assign a dimension to the object by saying, okay, a dimension of the object is just whatever dimension of the image, whatever vector space you associate to it. And that's my beta. Yeah. And essentially, as usual in this type of work, or as in the previous videos, even in this type of absolutely minimal assumption, again, minimal assumption to even make sense of my beta theorem. Yeah. What is the dimension anyway? To make sense of the beta theorem, the minimal assumption is this one but down here. And even in this kind of minimal assumption, we essentially have the beta theorem. And yeah, the only additional thing you need is a symmetric functor. But anyway, so otherwise, up to the minimal assumption, the beta theorem is actually still true. So that's kind of surprising, right? So essentially, as soon as you have a functor to vector spaces, your decomposition problem, the overall growth rate is given by, well, the dimension of your space. For any symmetric monoidal category with a symmetric functor to vector space. It's like a, well, rep G, let's just do the example of rep G. For rep G, maybe I can actually use a slightly smarter color here. What about blue, for example? Rep G, for rep G, my functor to vector spaces is just a forgetful functor. Let's just forget. I don't need to, right? So for all of the categories I've studied so far, the functor is pretty simple. It's just forgetful functor. But you can make this in complete general. Okay, so exponential growth is scary. Exactly the same statement, and actually exactly the same proof essentially go through. But anyway, so it's kind of this beautiful idea, or the beautiful observation, the beautiful empirical observation that things get actually, if you ask these asymptotic questions, things get really nice. And yeah, this really means it applies to representations of group, monoids, semi-groups, superversions of these. But what about more general categories? So what about categories where you don't have a functor to vector space? So this is kind of a large class of things that you can cover here, but maybe we are still somewhat in the realm of, yeah, representation of group things, because you have somehow a functor to vector spaces. But yeah, let's see how we can generalize this. And the answer is pretty nice. You just need to replace dimension by an appropriate different type of dimension, and you get the same statement. But anyway, take the beta theorem, keep the beta theorem in mind, just with dimension is now the dimension of the functor that you use to send it to some to vector spaces, and that's just the dimension of the object. Okay, same story as usual. It was really general. But let's now have a look at rapid counting a la Fibonacci. And I really like this illustration that I stole, because in this illustration, the rabbits are just cloning themselves. Everyone. And it would be so much better if we could just clone ourselves. So anyway, so you all know how the rabbit counting works. 1, 1, 2, 3, 5, 8, whatever. Okay, and you can do this with a matrix as well. And I call that rabbit counting a la Fibonacci with matrices. Yeah, so you just use this matrix m 0, 1, 1, 1. And then m squared, m cubed, m to the fourth will have the Fibonacci numbers in it. Yeah, 2, 3, 3, 5, you can already see it. And it goes on. So the growth rate of the entries is the growth rate of the Fibonacci sequence. And we already had that, or this is like super well known, and I kind of believe that you have seen that one before. It's the square root of 5 times the golden ratio to the n. In particular, even in this easy example, the rabbit counting example, the golden ratio, our beta, the overall growth rate, this guy here, is not an integer. It's not an integer, so it can't really be the dimension of a space. Yep, doesn't really make sense. So a category where you would have the decomposition rule, x squared equals x plus 1, which is exactly the minimal polynomial of the golden ratio. The dominating dimension is not, the dominating growth is not a dimension of a vector space. Yeah? Because the dominating dimension would be just given by, I mean, I just mimicked the counting in the Fibonacci thing, because if you just look at this matrix, yeah, here is my x squared equals x plus 1. So you just need to, here is my x squared equals x plus 1. I will explain the matrix in a second, it's already down here. And the B sequence is just the sum of the first column. So it will be a sum of Fibonacci numbers, so the growth rate will be the golden ratio. And how can we do that? Well, we can encode this fusion rule. So I only have two objects, 1 and x. We can encode this so-called fusion rule in a matrix by just writing down a matrix 2 by 2, where every column and row represents one of them, and the multiplication by x sends 1 to x, so I write this one, and the multiplication by x sends x to 1 plus x, so I write down this type of matrix. Hope that makes some sense. It's called the action matrix of multiplication by x. I just record multiplication by x in the matrix, and the column and rows are indexed by the indecomposables, in this case just 1 and x. That's our Fibonacci matrix. And then you can just think about for a second what this matrix encodes. So the power x to the n is encoded then in the first column of that matrix. So our sum problem is just taking the sum of the first column. And another way of doing this is to just write a graph instead of a matrix. That's equivalent data where, well, every vertex is just one of the columns or rows, and the entries correspond. Well, you have no loop here, so no edge. You have an edge from 1 to x, so you have an edge going in this direction. You have an edge from x to 1, so you have an arrow going in this direction, and I just simplify it to an unoriented arrow. And then you have a loop because you have an entry from x to x. So that's how you go between matrices and graphs. And if you have never seen this before, it's one of the most underrated facts ever that matrices and graphs are actually the same type of thing. And this is how it goes. Or let's say rectangular matrices. Let's say square matrices. Because just index the rows and columns by vertices, and every entry corresponds to an edge, essentially. So adjacency matrix, that's what people usually call it. Anyway, so that's a fusion graph, a fusion matrix. So in this problem, the leading eigenvalue of this guy actually determines the growth rate, because the leading eigenvalue of the matrix is the golden ratio. That's how it is defined. This is the characteristic polynomial that comes out of this matrix. And yeah, that's not an integer. So somehow this can't really work in the previous sense of, well, beta is always an integer. In this case, it would be the golden ratio. Cool. And this category actually exists. It's not just a toy example, and you can just realize it by representation of the mod 5 in characteristic 5. You just need to kill the projective ones, because there was a 3-dimensional representation, and if you were multiplying the 3-dimensional with itself, you got the 1-dimensional, 3-dimensional, the 5-dimensional, but the 5-dimensional is projective, and one dies, you get just x plus 1. That's how you realize that category. So what I'm trying to say here is actually not really important. What I'm trying to say here is I'm not coming up with any kind of a stupid example to convince you that my problem in general can't work. No, this is really an example. There is a category that has this multiplication rule of the Fibonacci, and it's called the Fibonacci category, accordingly to the multiplication being mimicking the Fibonacci numbers. So what can we do to address this problem? Okay, let's take a step back and let's look at something that looks very different. A random walk. So a random walk today we only do connected graphs in the oriented sense, because so this, as I said here before, the matrix is actually oriented. So the graph is actually oriented. I usually just don't draw orientations. So we take graphs in the oriented sense, and let's say they are connected. That's a simplification assumption that I will do here. And let's say we do some kind of and each step is chosen equally likely, so we do some random walk on my little graph. Not a Markov chain type random walk, but an adjacency matrix type random walk. So I'm not going to write a 1/2 or something on the edges. I'm really just thinking about a random walk where every edge is chosen equally likely. And we can ask the question, how often do we actually visit the vertex? Yeah, makes sense. And let's say I have some start point fixed. That doesn't really matter. If it's connected, you can choose any. So, but let's anyway, it's a little like with a fundamental group, there's a base point, but you actually don't really need the base point. Anyway, so there's a start point. Let's fix the start point, and we can ask the question, do we hit the start point again infinitely often in a random walk with probability 1, right? Probability 1, because we're doing random walks. One finds home. And people call that recurrent. And transient is the opposite, not recurrent. Turns out this is a 0-1 thing. You're either recurrent or transient, but it's not quite obvious from the definition. Actually, it is, because I have transient defined as not recurrent. But you can define it slightly differently. You can define it to say that you visit the start infinitely often with probability 0, and there's no probability in between. So it's again a 0-1 theorem. Anyway, for now, recurrent you come back, and transient, you kind of move away. Two type of problems you can associate to a graph. Yeah? A graph can now be recurrent or transient. Hope that makes some sense. Okay. Finite graphs are recurrent. Why? Well, because you only have finitely many possibilities to go somewhere, so finite graphs are recurrent. And as I said, I will assume that a graph is strongly connected, that's connected in the oriented sense. So this graph here is not strongly connected. It's just connected. It looks like it's connected, but I want it to be connected in the oriented sense. And this is a simplification. I actually don't need that, but it makes my life much easier. So let's just assume it. Anyway, random walks on finite graphs are always recurrent because there are only finitely many possibilities to do something. More exciting, clearly, would be random walks on infinite graphs. So let's say the easiest infinite graph I can come up with is this guy, the integer line. So just a line. 1D, it's usually called a 1D random walk. So take a step left, right with probability a half. And if you do that, and you ask ChatGPT to write a program that simulates a random walk, it will do the following, or at least that's what I did, and it did the following for me. So write some terrible Python code for me. I never tried that actually, to specifically say write terrible Python code. I only say write Python code. I should try that. Anyway, write some Python code for me that gives me pictures of the random walk and simulates them. And yeah, so this is like how far you are away. So you're at step 20 or something, and you're at step minus something and whatever. And this is kind of the distribution how far you are away. So you can kind of see at one point we are quite far away, but we're not that far away. We're roughly around 12 here. And yeah, sometimes we are here, sometimes we're not. But anyway, if you do this, what is the probability of return to the origin, of coming home? You can kind of see that in the graph, and everyone here probably has seen that at one point. It's a coin flip experiment. You will eventually, you should do some shit, but you eventually come back to the, and you eventually come back, and you eventually come back, whatever, something like that. So you can convince yourself quite quickly, and you can also do the calculation if you don't believe the simulation, that the probability of coming home is 1. So this graph is recurrent. Okay, so the probability of coming home is actually 1. Graph is recurrent. Do the same in 2D. Well, take a step up, down with probability. You do the random walk on the integer lattice, z squared, and it's a bit trickier. It's not quite clear. If you plot the absolute value of the distance, again using some terrible Python code and ChatGPT, the absolute value from the origin, it's not quite clear. It kind of looks like it doesn't really, it moves out or moves in. Here it's pretty clear. So by the way, here I don't need to take the absolute value, and it's kind of really believable that the random walk will eventually kind of stay in a non-zero area around here. No, sorry. The random walk will move outwards, but there will be some non-zero contribution around the origin, even if it's very large. And here it looks like there will be some non-zero contribution if you have taken very many steps. So this is just many steps taken. But it's not quite clear. So you get a bump here around here. Maybe this bump moves out. Not so clear. And yeah, so if you just do that without doing the calculation, you get an ambiguous result. I really can't tell. And if you do the 3D version, it's pretty clear if you draw the histogram. Yeah, this will move out. So the peak here after the certain number of steps is already so far out. So this clearly that the probability of coming home is smaller than 1. Yeah, it's kind of the same type of thing. And there's a famous theorem. It's Polya's random walk theorem. So z to the d is recurrent if and only if d is smaller than 2. Yeah. So d equals 2, the random walk on the integer lattice squared, so on the plane, is actually recurrent. So this usually the drunk yard finds home, but the drunken bird might get lost because in free space you actually will not find home anymore. And yeah, so this is a really cool theorem. It's not difficult to prove. So essentially, Polya analyzed the binomial distribution of the different paths you can take, and that's what comes out. So it turns out it's kind of a really clear cut between the low dimensional problem and the high dimensional problem. So in low dimensions, you will always find home, and in high dimensions, you will always get lost. Okay, and yeah, so little observation here as a side. Extending z to the d by a finite graph, which really just means put some finite graph somewhere, doesn't really change anything, because all of these recurrent transient properties are really for infinite graphs. So if you extend it by a finite graph, nothing will change. Yeah, so just as a side observation here. So here, if you look up Polya's original paper, it was about Gefahrtenstraßen. That's I will not translate that. But anyway, Polya was really just looking at the distribution of the different paths you can take from the origin, and this is a binomial type distribution, just in higher dimensional space. Hopefully it makes some sense here. You have some binomial type thing, 999, 3, 3, 3, 3. I shouldn't have marked all of them. It's too annoying. 1, 1, 1, 1, like this binomial type distribution. It's a very nice theorem, kind of surprising. Proof is not terribly difficult. Okay, so let's call one of our problems. So what does this have to do with our problems? Let's call one of our problems recurrent, respectively transient, if its fusion graph is. Yeah. So we have a fusion graph associated to our problem, and yeah, we just use the same terminology as from random walks. So this one, for example, is recurrent because it's fine. And then you have this following variation of Polya theorem, which is just really a tiny variation, so I still call it Polya theorem. So let's say we have our problem of our random walk problem for a completely reducible faithful group representation characteristic 0. So we are still in characteristic 0 groups. Then this is recurrent, the problem, if and only if it's virtually one of Polya's groups. And virtually means up to extension by a finite group. In particular, this is again saying the finite groups are somewhat very special, because up to the integer lattice and the integer lattice squared, the only things that are recurrent are finite groups. Yeah, finite groups. Extension by finite groups. It's a pretty cool theorem, kind of a generalization of Polya theorem, and gives us actually a good hint of what we are supposed to study, maybe in general. Yeah? So maybe we should look at random walks for a general problem, because we just recovered from Polya theorem one of the theorems I showed you before, where I had the growth rate is in theta or beta to the n, if and only if, and this is like the analog here. This is like the random walk analog. It's really nice. So Polya's version of our problem looks like this. Yeah. Example: if you do the fusion graph of SO2 with a vector representation, that's the natural number. That's transient. The number of paths moves out. So I've just plotted them, and you can kind of see here that the peak of the binomial will move out. So for the integers, remember Polya's paper, the corresponding number of paths would just be a binomial distribution. And here it's also a binomial distribution, but the binomial distribution moves out, and this number here, where it hits, is roughly square root of n. So it roughly moves out with the speed of square root of n. So n is 200, square root of n is roughly here the peak of the binomial distribution. And that's what it means to be transient. The number of paths moves out. So this one is transient. Finite groups are recurrent. And then here's a fun thing you can do. So for gamma and v, this is recurrent and transient. Well, arbitrary field, finite group, and any representation is recurrent. Arbitrary field, any finite tensor category, whatever that means, in the sense of ACNO, if you know what that means. Anyway, the large family of categories. every finite tensor category and any object and whatever, and it's transient, for example, in characteristic 0, any group that is not a torus of rank 0, 1, or 2, SL2, for example. Quantum groups move out and whatever. So most things are actually transient. So recurrent is a very, very rare condition, and it's again type of a theorem, and it's kind of a miracle that finite tensor categories, in the sense of Ettinghoff, of the tensor category book, Ettinghoff, Gelacki, Nitschik, and Ostrich, is any of those guys is actually also recurrent, and this includes representations of groups in characteristic P, for example. Right? This is absolutely not obvious at all. Anyway, so essentially everything is recurrent. That's kind of the conjecture I would make. But yeah, but I can't prove that. Anyway, so here comes the point why we want to study recurrent and transient things, because let me not go too much into details, but for recurrent properties, the beta theorem is still true. With beta the largest eigenvalue of the action matrix, and tau is 0, and h is a scalar. Yeah? So exactly the same as for the finite groups. General true, exactly the same type of statement as for finite groups is true for any recurrent problem. There's some annoying assumptions, but we ignore them. The recurrent problems behave still like finite groups. This is kind of the point. But I just showed you my conjecture that almost everything is not recurrent. So I spent at least 2 lectures on finite groups and it was completely wasted because essentially nothing is recurrent. But of course, it was still not wasted. I'm just kidding. All recurrent problems we have seen so far. And you can write down an explicit formula, and I have it on the slide, and it's really easy. It's just using eigenvectors and eigenvalues of matrices to get the scalar in front. But let's not worry about it too much. You can just do it. You can, for example, symmetric groups. The only thing you ever need to know is this graph, and you can just do it from the graph. You calculate the eigenvalue, you calculate the eigenvectors, and then you get the corresponding growth rate. And you can do that for literally anything you want. And I have a lot of examples here on the slides, and the slides are available if you follow the link in the description. But I don't want to go into this too much, but you can do quite a few calculations. So the growth rate is always exponential for essentially everything, just that our scalar doesn't need to be the dimension anymore, the overall growth rate. It's the largest eigenvalue of the action matrix. Anyway, and this really also applies to infinite graphs. So let me just kill it here. So let me just wrap up. So I also did the hacker category, but I haven't explained what that is. In the live lecture, I actually did, but in this lecture, I'm not going to do it. As I said, the slides are in the description. Let me rather wrap up what we have seen. So essentially, everything grows exponentially, what you can see, and there are very general theorems, and the correct replacement for general monoidal categories, what you're supposed to do is you're supposed to look at the leading eigenvalue problem, and then the dimension will be the leading eigenvalue, and you can get the h from you can get the h from the eigenvalues and as eigenvectors of the matrix, and the tau, I haven't explained that. You can get the tau as kind of the drift factor of the random walk. Anyway, I hope you enjoyed this video, and I'll talk to you next time.